It's great. So let's get started. So just a reminder again, everyone. So thanks for everyone for so mass today. We are still in the COVID exposure protocol. I don't have exact data on this, but I think there were 2 or 3 COVID positive cases in the class. They might not all be connected. They might have been because of the fall break. But I think if we don't get any more positive cases, we should be out of the protocol next week. So hope everyone's doing well. Those have been only the reports I've heard, but just so FYI on that. And so let's see. So yeah. So today we're going to, the plans to start the new section on dimensional reduction. Before we jump into this, just to go over the schedule and the logistics. So the homework 3 was due on Tuesday. I had a bit, a number of people have not been able to turn this in yet. If you haven't, please do so. I know this one and the next one will be kind of the longer of the homework assignments, where some students have a bit more struggle on those. So that's okay. I think the material is important. It's important to do. It's okay to have some hard stuff occasionally. Hopefully, overall, the class is moving at a good pace. But so the good news, if you've had a little trouble on this, we'll try and grade them. Hopefully everyone does great, but a reminder, you do get to drop the lowest score on your homework. So I have, however, put a condition that you do need to turn in and make an effort on all of the homework assignments in order to drop the lowest one. I don't want you just to skip a whole section of the class. So if you haven't done it yet, please turn something in. We'll try and grade it and give you some feedback on that. So I want you to learn all of this material. And homework 4 will get out early next week, and that will build on homework 3. So again, if you didn't do homework 3, you should try and put an emphasis to try and get your understanding on that part. And again, because of various things going on, we won't be able to start grading those until this weekend, but we'll try and get those graded soon. Other thing is quiz 4 is today. All right, so if I'm still kind of lecturing on about 10:35 or so, when we are supposed to start the quiz, please stop me. It will be on gradient descent. So the previous 3 lectures, you will get a cheat sheet, so have that ready. And as usual, you'll have until the end of the day to take it. It's on Canvas. I encourage you to take it early on, because then myself and the Ts are definitely available to answer questions. I kind of had the impression that I felt like I went through the gradient descent stuff a little brisker pace than I'd had anticipated. I guess I threw in some bells and whistles, and that kind of meant everything else went a little bit faster. So since the quiz is today, before I start on dimensional reduction, I want to see if there are any kind of questions or things I can clarify. I was chatting with someone who had some question about this before I got started. But if you have any questions before the quiz, or if anything I can go over, that would be helpful to you. In the back first, yeah. So when I was trying to do the homework, I was trying to do it 3D really well, right? And I realized I have no idea how to do the line where you get the best value of gamma Oh, so the line search. Yeah, yeah. So, okay. So gradient descent. Again, we're trying to learn these parameters. We have some function from RD to R, and we want to find the arg min alpha in RD, and we set alpha equals to gamma alpha minus gamma k, the gradient of f at alpha, right? And so you're saying there's a line search how to choose this best so value of gamma that tells you how much you're moving, right? And okay, we can think of having this function, right? And oh, not like that. Okay, so we have this function, and we will start someplace at alpha, and the gradient will give us some sort of direction. This will be the gradient of f at alpha. And then the gamma parameter, well, this is the negative of the gradient, right? So this is the negative of the gradient. We subtracted, the gradient goes up, this goes down. And we want to know how far to go. And that's controlled by this gamma parameter, right? And there's this method called, so line search of choosing this. And this is the idea that once I've chosen this gradient direction, then my algorithm, all it can do, instead of moving in this d-dimensional space here, it's restricted to this one-dimensional line where it's moving, and I can just try and solve for the value of gamma, which is doing the best here. And there's going to be some sort of optimal, right? This corresponds with alpha minus gamma, let's say star, and that's the one that minimizes this so cost, right? And if I can do this every step, then I should be able to do as good as possible in this least number of steps, although this might be expensive, right? Okay, so this is, again, allowed me to review kind of the procedure of gradient descent. How do we do this line search? Yeah, so there are a variety of ways how to do it. The method I describe in the book, which I did describe in detail in the class, was to do what's called this thing called golden golden section search. And I might not get the details of this exactly right, but the idea is once I've restricted to this line, right, this is the value of gamma I can choose, there's going to be this corresponding function, and I'm at a point, you know, I'm at here, this is gamma equals to 0, I'm at this value, and I want to figure out where the function along this line is the minimum. This point would correspond with this optimal gamma star. Okay, and so what I would do is I need to evaluate a few places. So typically what I'll do is I'll pick two choices. I have the original choice, I have another one, and a third one, A, B, and C. A, B, and C, okay? And now, if I have kind of a few options based on the function value at these points, this is f of A, this is f of B, and this is f of C, okay? And so if I know if B is less than no, I think I need one more point here. Let's call this, let me add in a point D. Let's call this, yeah, so this is A, B, C, and D. Okay, so this would be f of D, f of C. Okay, now I know if, so I have the order of these points. I know if f of b is less than f of c, then the minimum must lie between a and c. But if b is larger than c, then the minimum must lie in here. This is assuming the function is going to be convex. This works, but people use it otherwise. So I can basically say if b is, or f of b is less than f of c, then I know gamma star, that gamma star is in the interval AC, right? So I've reduced the interval that I can consider into this region. It's somewhere in here, and then I need to choose some other point. Okay, and how do you choose this point? It's not, you don't want to, now I have three things. If I choose the middle, I might get E again. So I end up wanting to choose, I'm going to guess it's on this side and choose another point over here. But then if instead f of c was less than f of b, then I would know it would be in this interval instead. It's other from b to d. And this allows me, it's not quite cutting in half every time, but if you choose these appropriately, you cut it at the golden ratio, which is the best that you can do. Right, and the exact way to choose them is in the book a little bit. But if it's convex, then this allows you to kind of zero in on this range. Okay. Okay, I'm guessing you probably had a different question.
Yeah, just more on based on, I guess, what we just kind of went over. What are we expected to show on paper, I guess, for the quiz?
Yeah, so you should know roughly how things about functions. What do we talk about, the properties of functions? If I give you, I'll give you something that I don't want you to have to do a lot of calculations on anything, right? But the properties of functions, that should be something if there's a picture or a very simple equation, you should be able to work it out. You should understand this equation, how to use it. Should understand, I don't think I'm asking you how to calculate the derivative, but you should know how to use the derivative or the gradient. But if you're given the gradient, you should know how to use it. Okay. Calculations are something that's more of a homework sort of question. But if you're given that, you should know how to take steps, right? How to kind of use this and stuff kind of like that. Does that help? All right. And then let me just say one more thing about the gradient itself. The gradient of f, right? This is an important thing. It goes from RD to RD, and it's given a function of f, and it's actually, right? So I'm going to be taking in a value alpha. So alpha is going to be in RD. That means alpha equals alpha 1, alpha 2, up to alpha d. And this is going to be all the partial derivatives. Okay, so if you've done a derivative, then you have a bunch of variables, alpha 1 over alpha d, but what it does, the alpha j, partial derivative alpha j, this basically says alpha I for I not equal to j is a constant, and then you just take the derivative with respect to the one thing that's not a constant. So if you're polynomials, then you should be able to do this. And we've gone through an example that knows if you're confused about that. And we do this for each, we get to do this d times and we get d values, right? And this tells us a direction that we're moving in, right? So again, looks like this function, if we're at a point, this is in kind of R2 in this example. And so I'm getting a direction that I can subtract from a point, so it's giving me a vector, right? So it's in the same dimensionality as the space here. All right, yep.
So for each step in the iteration, we can choose to get the gamma of each step.
Yeah, you can choose a different gamma for each step, and that's why I put a subscript k here, because at the kth step, you might choose a different gamma. And so the line search, which is here, which is kind of this the way of implementing that, the line search, it chooses kind of whatever it thinks is the best one at each of the steps.
I want to ask about that, just like whether constant gamma or like the gamma each step.
Yeah, so I guess it,
So like,
can you say that again?
If the golden section search was for the gamma for each step, or it often just a constant.
Yeah, this is for a gamma for each step. Every step, I get this green line here that I've restricted my movement to. The direction of the gradient restricts myself to a line, and then I can search along the lines. In one dimensions, I know how to do this. In multiple dimensions, I can't do this kind of this grid search or the searching thing. So that's why I use gradient descent in multiple and higher dimensions. But once I've chosen the derivative, I'm restricted to one dimension. So it's meant that this dashed green line here corresponds with this green line and the x-axis of this picture on this slide. Yeah. Great. And let's see in the chat, could we go over the Lipschitz again? I would love to see an example where it's important to use and how it irritates to so convexity. Okay, great. So the Lipschitz question. Okay, so the Lipschitz, okay, so a function g from Rd, let's say, to Rk is L, so Lipschitz, this is something that a definition that comes up in a lot of places in data and functional analysis. If for any PQ in Rd, that we have the following property, that the function value at P minus the function value at Q, right, that this is less than L times the difference between P and Q, right? So if P and Q don't move very far, if they don't move very far, then the function value also can't move very far. And this is controlled by some parameter L. So that means it's L Lipschitz here. And so you can, it might be useful to rewrite this as G of P minus G of Q divided by P minus Q, right, is less than or equal to L. And you can think of if Q is equal to P plus some H times U, where the U is a unit vector, then this went back to the definition of the directional derivative, right? That said then this this quantity here is H, right? So as I move these closer together, then the function value changes by some kind of the amount the function value changes should also depend on H. So it's basically the maximum norm of the gradient. What is L again? L is a parameter that I'm saying. So this is a property. I'm saying it's Lipschitz if there exists some L which is a constant, and if I know what that constant is, I can call it a value, and I call it, okay? Okay, so this is, I defined it this general way because you'll see this Lipschitz constant elsewhere, but this is interesting. This is most interesting when we think of G is equal to the gradient of F, okay? And so we want the gradient of F to be L, so Lipschitz, okay? And then that corresponds, if the gradient of F is L, so Lipschitz, if I can write, let's see if I can get this right without my notes, if let's see, if F of P is less than or equal to f of alpha plus some sort of, let's see, there's some sort of linear term. I think we say L over 2 times P minus alpha, right? So P and alpha are then these two values. Think of P and alpha now in RD, right? So this is like the P and Q. And so this is squared here, right? So this turns out to be the L Lipschitz term here. I think there's another linear term I need to put in there. But the idea is that this function, it has to be something convex, and so I pick some point alpha, and I look at, this is the point alpha comma f of alpha. Okay, and I can do a quadratic approximation of this. Okay, so there's some sort of quadratic approximation of this, which looks like this. I can always put a nice parabola here. This is a parabola that is always above it. So f of p, so if I evaluate now at some point p, and I look at the function value, this is f of p, and this point is going to be f of alpha plus some linear term that you can find in the notes, plus some sort of quadratic term. And I think the linear term is just the gradient times the distance. And so there's this nice function that's a parabola. F does not need to be exactly a quadratic function. It could be like a quartic function or something. But there's always this parabola which sits above it. There's always a parabola that I can put it at the tangent point, right here, and this curves, and this is going to curve more. It's going to curve faster than the underlying blue function. And if I know that I have this with some value L, then I can guarantee something about the convergence rates. Okay, I can say that if the choice of my gamma, of where the gamma is the learning rate, is below 1 over L, then this will converge at a certain speed. I will get epsilon error after roughly 1 over epsilon steps. Okay, and so I don't necessarily know what L is, but if I have this property, I know it will converge in some nice way. And then if I have the strongly convex, which means I have a lower bound as well, right? If I have a strongly convex part here that sits underneath it, right, another parabola, then I can guarantee that's going to converge at a rate which is even faster than this. And then I can find that by doing this adjustable rate thing, where I start large and I adjust it based on this condition. So it's kind of more of a property than something that directly tells you an algorithm. But a lot of the setup we will create using from data will give us this property. Yeah.
So at this point in your lab, actually, that you also said that functions were eta strong.
Yes. Yeah.
What is the eta?
Right. The eta is the counterpart to this L, but that tells me it sits underneath. Right. So it means that at every point, so at each point alpha here, right? For every point alpha, I can sandwich the blue function, which is what I want to optimize, in between a green function and the peach function. I can sandwich in between them, and they're both these polynomial functions of degree 2. Okay, and the coefficient in front of the degree 2 part corresponds with the L Lipschitz for the part that's above it, and the eta strongly convex for the part that's below it. Yeah.
So that's what we do with it. Like, what do we do?
Yeah, so sometimes because of how you've set up your data itself, like so I think if you go back to there are two answers to this. So one is if you look at how we derive the function f from data, it's going to be a bunch of these quadratic terms, and we're adding these together, right? And so the amount we add together is going to contribute. Each term is going to it's going to be a sum. Each of those terms is going to contribute. F is actually going to be a degree 2 polynomial function in that way. Okay, and the sum of all the terms we add together, each of those that have a quadratic part, will kind of be contributing towards the L or the eta in our F. So the value, the coefficient F. And if we know, if we were to write all those values out, then it will tell something about it. So it's going to depend something about how far away the points are from where we're optimizing. So if you say all the points are in a certain region, you can get some sort of bound for these things. People typically don't do that, but you could try and work out an upper bound on this from properties of your data. The other thing we do is we have this adjustable rate a way of learning, where we start with a large learning rate, and if we guess something too large, we'll be able to identify that and keep shrinking that until we get a learning rate which is kind of in between the L and the eta, or in between the 1 over L and the 1 over eta. And once we get there, then we're going to get the very fast convergence. So it kind of explains why this adjustable rate learning algorithm actually works. Without looking at my notes, I'm not going to be able to write down the exact form of the adjustable rate sort of learning function, but it kind of helps inform that, right? So it's not really an algorithm, it's kind of helping explain why the very simple algorithms that I had the formula before are actually going to work, and why we can get fast convergence. All right, so great. So hopefully that was a good review on this stuff, and help kind of go over some of the parts we went kind of so quickly through. All right, so let me try and cover some stuff for dimensional reduction at this point. And we've got a few more lectures, and the stuff at the back end we could probably skip if we don't get to it. So I think that's going to be okay. But we are starting a kind of a whole new section here. And so my goal today will be to introduce the problem definition and why we're doing it and when you can do it. And we will talk about kind of a black box version of the method in the next lecture. Then we'll see an algorithm that will allow you to do it, and then we'll see some use cases of it in the final lecture. Okay. Okay. So, all right. So the goal here is we're going to have n data points in RD. Okay, so we have n of these data points in d-dimensional space, and basically we're going to say d is too big, and I'll talk a little bit about what this means, but I want to kind of give a little bit more notation and context first. So we want to somehow, it's going to be hard to deal with it being such a high dimensional space, right? First off, it's a little bit hard to conceptualize high-dimensional spaces, right? So if our data could somehow be in 2 dimensions, we can draw pictures, and that's really nice. And this is actually one of the goals of doing this. Okay, so we're going to model this. So I could think of these. I'll say these are A1, A2, up to AN, and these are all elements of RD, right? These are d-dimensional points, and I can't really even draw them, right? They're high dimensions. Think of D as Could be thousands of dimensions here. But even thinking of 100 dimensions is probably sufficiently challenging. And I'm going to write these as a matrix, okay, R n cross D. So this is an n by D matrix. So I'm going to draw this like here. And so this direction is going to be n. This direction is going to be D. So I'm going to have n rows. We're going to think about this having even more rows than we have columns. So the number of data points is even higher than the dimension here. There's some cases where you want to flip this and that'll be fine, but we want to reduce the dimensions. It's like 100 dimensions, but we may have like 1,000,000 data points. Okay, we still want to understand that. Okay, so this will be one. So data point, this would be like AI, right? Remember, AI is an RD, right? And so I'm going to think about this as a matrix. I'm going to take all the data points, I'm going to put them in the matrix, and I can't draw pictures, right? So I can't use as much geometric intuition as I typically like to use. I really like geometry. But we'll do the next best thing, I think, which is linear algebra, which is still pretty good at introducing these things. There's some people go through this, could teach the whole stuff in this class with just like probability theory, and I find that more confusing than the way I'm presenting it. Okay, so we're going to go use linear algebra to try and handle this. Okay, and okay, so before, yeah, so I'm going to talk about a number of examples where this might occur. Okay, so think of, so one example, I'm going to have n, so weather stations, stations. Okay, so n weather stations, and I'm going to have D kind of, times where I measure the temperature, right? So each row is a weather station, and maybe over a month, every day at noon, I measure the temperature. Right, so there's a group in the atmospheric science department that I've worked with that they help monitor like 40,000 weather stations around the U.S. and at least every hour, sometimes more frequently, including some on campus, they'll get the measurement of the temperature, and you can put these all inside the matrix here. Okay, but understanding all the temperatures will help. It's hard to understand if I have 40,000 for n, and I have like a month or 3 months of data, I want to see how things are correlated with each other. 100 dimensions might seem kind of hard to deal with here. Understand the relationship between the sensors other than their geographic position. How do they one depend on another? Okay, another common example is I'm going to have n. So let's say Netflix users, and there are D movies in their catalog, right? So there are, I don't know how many people in the US subscribe to Netflix. Maybe there are 50 million different subscribers to Netflix. Maybe that seems probably not that high, but maybe let's say 10 million subscribers to Netflix in the US. And how many movies do they have in their catalog? It's probably less. It's probably less than 50 million, but it's maybe it's 100,000, right? And everyone gives a rating, right? They used to allow you to rate movies. Now they kind of gathered this in other ways, but there's somehow some sort of measurement of how well someone has interacted with it. Maybe you just watched the preview that gives a score of 1, which is good. Maybe you watch the whole movie, that gets a score of 10. Maybe if you watch it 3 times, then you get a score of 10. You watch it once, you get a score of 7. You watch half of it, score of 3, right? They kind of infer how much you like the movie by your interaction with it. And so I know a lot of them are 0, maybe you haven't seen it, they're deep in the catalog, but there's this big matrix of things, and every entry is some sort of numerical value. And they give you some score of your interaction with the movie. And they want to predict how well you'll interact with other movies, right? Okay, one more. Let's say I've got N stocks I want to track, right? I want to N stocks in the stock market. And let's say that there are, D is going to be a little bit weird here. I'm going to start by saying, actually, I have uppercase D, days of kind of data. So think of the closing price at the end of the day is typically what's used, right? So the closing price. Okay, and instead of this, let's actually change this to just one stock. So I'm going to change this to one stock, and I'm going to do this. There's this cool transformation. I think someone asked me about time series and how this fits in here. So let's say I've got one stock, and I've got the closing price every day, right? And I'm going to have for D days. And what I'd like to do is turn this into a matrix. And what I do is I want to pick some time window where I want to say, I want to produce, eventually I'm going to want to kind of predict the value in the day D plus 1. And what I will do is I will take the previous D days, right? And so I'm going to say the previous D days are going to be A1. And this will be the first row in my matrix A. Okay. And then I want to do the same thing with the next day. I want to kind of overlap these. So the next day, I'm going to pick another, this will be A2, and this will help me predict this day over here, again, the following day. So I want to use A2 as then an overlapping set of D days here. And so I'm going to get so that in total, the N is going to be D minus, let's say D, right? So the number of days for every starting point up until kind of this last kind of, there's some last region of D days here. Every starting point, I can start a new row here, right? So this would be AN, this would correspond with AN, this last row in this column here. Okay, so I'm taking a time series and I turn it into this matrix. Okay, and then I want to understand kind of some pattern over a sequence of D days. Okay, again, so this is this and then more advanced things on this is a very common thing inside of like econometrics. But again, I'm going to get this big N by D matrix. I may have a lot of days and I'll pick a shorter interval. You could also take N different stocks over D days and stack them up. That's a simpler way of getting a N by D matrix here. Okay, so I want to, before we jump into what we're going to do and why, I want to identify a few properties that all of these have. First of all, the first important property that I really want to highlight is that all kind of columns, all the attributes have the same, so units. Okay, that was true in the case with the weather. They're all temperature, so I was all measuring them in Fahrenheit, for instance, right? I wouldn't mix Fahrenheit and Celsius. I didn't throw in the temperature and also the wind speed. They also these often measure the wind speed also, but I'm not going to talk about mixing these things together in this context. Okay, with the movie ratings, they were somehow the same unit. There was somehow a user versus a thing. every user had some rating, inferred rating of a movie. And here I have the closing price. Every entry here in this matrix is a closing price, so I can compare them. Okay, and so this is important because I'm going to be taking a distance. I'm going to be comparing something like, let's say, AI minus AJ, right? I want to take the Euclidean distance, and if we remember what this means, it's going to be J, let's say, I've used I and J already here. So let me say, two entries here. These are A and A prime. Okay, and I'm going to say, I'm going to compute this distance of J equals 1 to D of AI, that's the index, the ith entry, the jth entry minus jth entry prime squared the square root. Okay, so if two columns represent different units, like the height and the weight we used in our earlier example, well then I can compare two different rows, their elements against each other. But when I add them up, if I were to add, when I'm adding up something that measured the difference in height and something else that measured the difference in weight, I'm kind of mixing units again, right? And this would be nonsensical. Okay, so what we're going to be talking about are matrices. I'll call these data matrices, where all the columns are measuring kind of the same quantity, and it makes sense to add them up. Okay, so I should be able to do this. So I want to highlight that. You'll see a lot of textbooks and a lot of classes that will use like this. There's this iris example of these properties of a flower, and they run dimensional reduction on that example. And that makes zero sense, because if I change the units from centimeters to inches, it changes the results without changing the data. Okay, so it's really important to keep this in mind when you're working with this. Was the inside the parentheses, this is can rewrite this. This is AJ minus AJ prime, and that was the idea that this guy was equal to A1, not alpha 2 up to alpha AD, and this guy was A1 prime, A2 prime up to AD prime. And these are both, think of them as both rows in the matrix, but we'll think of them in some other, we'll use this distance in some other context too. Okay, great. Okay, good. All right, so our goal is going to be finding a lower dimensional representation. We're going to reduce the dimensions. And again, this is going to force us to mix these dimensions together. And if they mean different things, this won't make sense. The other thing is that these are all common scenarios where there are actually smaller dimensional properties going on here. There are correlations among these things, and it's very common to reduce the dimensionality before doing some sort of analysis. Okay, so let me cover projections today. Okay, and so this will be a review from what we talked about with things like dot products, but it's really important. So I'll probably do it today, and then we'll review it again in the next lecture as well. And I'm going to think of having a point in RD. I'll think of it as a point in R2, and I'm going to have a unit vector V, which will be also an RD, but with the restriction that it's a unit vector. So to have a unit vector, remember it's going to come from the origin, and it's going to be a length 1 unit vector, but it will kind of induce this line. Okay, and we want to remember what's going on with the dot product between V and P, right? Remember, this is going to be I can think of this as finding the closest point of P onto this line and measuring this length. So this is this length is equal to the dot product between V and P, given that V is a unit vector in this case. Okay, we're gonna really dive in and really use this sort of property. So this is this magical property of the dot product. And again, we're going to call this point here, this is going to be the projection on V of P, right? And we're going to say that the projection of V on P, we're going to define this as, again, V dot P, which is a scalar. This is just the length, but then I'm going to multiply it by the vector V, right? So that vector V, it tells me, okay, I'm on that vector V, and how far am I going to go? If the length was 1, I'd be right at the tip of the arrow. But if the length is going to be a little bit larger than 1, let's say 1.2, then I'll be about at that blue circle where that projection of V onto P is. Okay? Okay, so this is a projection. Okay, and this is a projection onto a one-dimensional vector, and this works, I drew a picture in 2D, but this works in any dimension, right? The same picture kind of exists in any dimensions. And the trick is we want to do this not onto a one-dimensional space, but onto a k-dimensional space. Okay? So now I'm going to have I'm going to use B. Oh yeah. Yep.
What was the symbol you're using for projection?
This is a pi. Yeah, it's a pi. Yep. Yeah. Yeah, that's I guess pi kind of is like has a P in it, and that's where the projection, that's where it comes from. Yeah. So okay, we're going to do this for a b-dimensional space. This is going to be or a k-dimensional. So subspace. And I'm going to kind of use B as just kind of a symbol to represent this. We're going to say it corresponds with an orthogonal so basis, and I will call that VB, and that's going to be, when I do VB, this is going to be a set of V1, V2 up to VK, which will have the property that that Vj, each of these vectors is going to be a unit vector, that Vj, Vi is going to be 0 for j not equal to I, right? So if these are different vectors, they're going to be 0. That means they're going to be orthogonal with each other. Right, so there's a right angle between them, and this is true. It could be in high dimensional space, but it keeps this right angle property. And I see your question. And then, yeah, right. Okay, what's this question? So you'll basically project every point onto a dimension lower. Yeah. So we'll get to reducing the dimensions in a second. That'll be the last thing I get to today. Okay, so now this will allow us that for any point x in B in the space that's in this space, I can write x is equal to the sum, and this is going to be how we're going to do this projection, equals to 1 up to k of alpha j times Vj, where in this case, alpha j is going to be equal to x Vj. Okay, I'll be able to write, I'll have, if the orthogonal basis means that any point in the span of these vectors, any point x, I'll say in B as well, I'll write that. I can write it exactly, I can recover it by some coefficient times these vectors. Okay. Okay, and if it's not on this, okay, so now the question is, what do I do if for a point that's in RD that doesn't happen to lie in this special subspace. Okay, and that's going to be this projection. Okay, and so for X not in B, right? Then I can project X onto B as, I'll write this as, again, pi of B of X. Okay, and this is a point X in RD. Okay, write this as, again, exactly the same way. Vj of P Vj, right? Which is exactly the sum of j equals 1 up to k of the projection onto Vi of P. Okay, so if I'm in, I can think of having a space here, right? So this space, this point here is the origin. Okay, and I can think of filling in, there's a space here, but actually, I'm actually living in so I'm actually in R3, right? I'm in R3, but there are these two vectors that are coming out. So think of it as two-dimensional space. And then I'm going to have a point X, which does not lie on the space. So I need to project it down onto here so that this is a right angle projection onto B of X is the closest point. And basically what I do is the same way as if I were to recover a point in the span, well, I do the best I can. I find the closest point in the span. I just try and recover it, and there are some parts that are missing. Okay, and so I'm getting some point X, and I'm projecting it onto the closest point in that space, and that's exactly on a projection onto each of the bases. Right? When I do this projection onto a single point here, that projection is still a point in RD because I'm multiplying by the vector B, right? So this is still in RD here because the dot product is a scalar and V is a vector in RD. Okay, so when I'm doing this here, I'm getting these projections where each vector is in RD and I'm adding them up. The same way, if I'd chosen the vectors as the orthogonal basis, where there are the things with all zeros except for a 1 in that axis, I actually recover kind of the coordinates of the points, but I'm just using a different basis here, a basis that is defining my B-dimensional subspace. And so this is how I project in this space. Okay, so let me just state the goal of what we're going to be doing, and then we will we'll stop here. The goal is kind of given A1 up to AN, find B of dimension K to minimize the sum of squared errors. This is equal to A of AB, which is going to be equal to the sum of I equals 1 to N of the difference now between AI and the projection onto B of AI, square all these. So we're using the sum of squared errors again, and we're going to trying to find the B and the B is defined by these K basis vectors that minimizes the sum of these projections. Okay, that's what the dimensional reduction, this is the most classic formulation of, there are other formulations. This is the most classic one. This is one that has the best algorithms, frankly. And so this is what we'll be studying for the next few lectures. Okay, so hopefully helped you define it, understand it. We'll go through kind of a little bit more in the definitions, review this, and then talk about how you do this using linear algebra to some tricks to solve it. Okay, we'll stop here, and open up the quiz, and I will be around for questions. Yeah.